Okay, the time now is 8:45. I don't think everyone is here though. All right. So guys, how was the quiz? Like, is it easy? Is it too hard? I think it's kind of straightforward, right? Okay. So now we have 10 participants. All right. So this since this lecture is going to be recorded, I think we will start now and we will keep to our time. Okay. All right. So those who have attempted the quiz, congratulations. You have attempted your very first quiz for this semester. If you got some of your answers wrong, no problem, no worry. We have many more quizzes like this. You can expect this kind of quiz to be in every class. Okay, so for today's class, we already have one quiz, so I think we'll not have another one. But for our next class, we have one for each class, right? All right. So hopefully this quiz also allows you to think a little bit. And I've also posted PowerPoint for your reference actually, but I'm not sure how many of you actually saw that PowerPoint. Right? You can always use that PowerPoint to refer and answer the quiz. Okay, the other thing about the quiz is that I'm not sure if you guys noticed the deadline for the quiz. I actually give it a little bit more generous deadline, which is 1 day. Actually, I realized that some of you are attending this class from another time zone. So you might not be able to attend the class like in real time. So you have actually 1 day to answer the quiz. Right, so hopefully that will help you guys to follow the class better, right? Uh, right. So if you don't feel like you understand enough and you want to answer later on, yeah, you can always do that actually, as long as you're within the 1 day time. Okay, so let's continue with our topic today, and it's 8:47. All right, we are on time, and this is your attendance again. If you haven't scanned your attendance earlier on, you can scan it now, and I will not display this QR code until the end of the class again today. All right. So in topic one, just now we have seen what's the difference between analog signal and a digital signal. And as I said just now, going forward in this course, we are not going to talk about analog signal anymore. We are just going to talk about the digital signal. Okay, this course is called digital logic after all, right? And one of the fundamental concepts in digital signal is knowing how computers talk to one another. Okay, how computers communicate with one another. And yeah, you can bet that the computers communicate one to one another through digital signals, right? That is what we understood from the last topic. But in what form? So computers cannot understand like language. Okay, for example, if I type in the chat, hi, H-E-L-H-I, okay, hello, Hello, the computer will not understand this alphabets. So instead, what the computer will do is that it will take the alphabet and then change this alphabet into a number. And then the computer can perform operations on the number. So computers are very good at crunching numbers, but computers are not very good at understanding things other than numbers. Okay, so because of that, all the digital signal that we talk about is going to be in the form of number. Okay, number. All right, and that is why the very first topic that in this course, okay, not the very first, the second topic, but it's the very beginning, is number system. Okay, number system. The number system is the way computer talk to one another. Okay, let's take a look at an example over here. So for a human, if I'm talking to you from one human to another human, and the medium that I'm using right now is English. Okay, so we use language. Okay, we use language as a medium of communication. Like it can be English, Malay, Tamil, Chinese, whatever. Okay, any language, that is the medium of our communication. But if I have one computer and I want that computer to talk to another computer, what is the medium? Computers cannot use language. Computers don't understand language. Computers understand numbers. Okay, So that is the definition of number system. So number systems is a way to express numbers. Okay, just like language system. So language system is a way to express your intention. Okay, so a number system is the same. It is a metaphor. It's the same way. Okay, so let's take a look at how a number system works. So okay, over here we have a computer, and we want this computer to talk to another computer, okay, across the internet. So, and it needs to use a medium, and that medium is going to be number system. All right. So just like in a language, right, we have so many kinds of language. So in number systems also, we actually have many kinds of number systems. So which one we're talking about, right? So these are the most commonly used number system. Okay, over here we have decimal, binary, octal, hexadecimal. Okay, some of you might have come across this. You might have come across a decimal number system. This is the number system that we are using, like right now. Like we are taught this decimal number system since we're a child. Okay, but maybe you're not so familiar with other number system, binary, octal, and hexadecimal, and that is what we are going to cover in this topic. So let's take a look at what is the difference actually. What's the difference between all these number systems?
Sir?
Right. Yes.
You
Question?
need to share your
I
slide.
can't see your screen, sir.
Oh, okay.
Yes, we can see your
Oh,
slide.
all right, all right, all right. Yeah, that's a good thing. Luckily, you told me about it. Like, otherwise, I would have gone to Rambo.
Now can see, sir.
Okay, now you can see, right?
Yes, sir.
Oh, that is strange. Okay, thank you very much. Thank you very much for that. I didn't even notice that. Okay, so actually I've gone 2 slides without. Okay, let me just go back a recap. Okay, so a recap. Just now we were talking about humans talking to another human using a language number system. Okay, you guys are seeing this slide, right? So now, what about computer? Computer talk to one another using using this number system as a form of language. Okay, so in number system we have a few language, or not language. We have a few format. Okay, so the first one is called the decimal number system. This is the one that we are familiar with. We are taught this since we're a kid, and we also have other kinds of number system which we are going to cover in this class. All right, so let's just take a look at how are they different. Okay, so this is how how different number system count. Okay, these are the digits that is allowed in a different number system. All right, so let's just take a look at the one we're most familiar with, which is the decimal number system. Okay, so a decimal number system is also known as a base 10 number system. Okay, base 10 number system. So why is it called base 10? If you take a look at the digits in a decimal number system, so you have these digits from 0 to 9. So you can view this digit as a symbol to represent the value. Okay, a symbol 0, symbol 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many in total? How many symbols do you have over here? You have 10 symbols, right? You count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are a total of 10 symbols in the decimal number system. So that's why it's called a base 10 number system. Okay, decimal number system, base 10 number system, they mean the same thing. Okay, clear? Now let's take a look at okay, the first one over here. Let's take a look at the binary number system. So a binary number system is also known as a base 2 number system. Base 2 number system. Why is it base 2 number system? Because in a binary number system, there's only 2 symbols that it can recognize. There's 2 digits that it can recognize that's allowed in a binary number system, and that is 0 or 1 only. Okay, so you might find it a little bit strange. Okay, 0 or 1 only. Okay, so bear with me on this one. Is there such a thing like a 2 in a, write this down here, a 2? Is there such thing as a 2 in a binary number system, there isn't. Okay? There is no such thing as a 2 in a binary number system. So you have 0 and 1s only. Okay, what about octal number system? So in octal number system, octal, in other words, it's also a base 8 number system. So in a base 8 number system, these are the allowable digits. These are the allowable symbols. So these are the symbols that you can recognize in a base 8 number system. You can think about this as a language, right? So in certain language, you only can have a certain phrase or certain words. Okay, so some words are not recognized in different language. Okay, so for example, if I say hello, hello is in English, right? If you were to change to another language, let's say if I speak Malay, okay, maybe Malay has the word hello. Okay, if I speak Chinese, there is no such thing as hello in Chinese. Okay, so that's the same thing over here. So 0 and 1, it exists in a binary number system. It exists in an octal number system. But if you have a 2 over here, 2 doesn't exist in binary, but it exists in octal. It exists in other number system as well, right? So for octal number system, same way, we have 0 up to 7. In total, we have 8 symbols over here in an octal number system. Decimal, yes, we have 10. And what if we go beyond 10? So we also have this strange looking number system over here. It's called a base 16. It's the base 16 number system, and it's also called the hexadecimal number system. So what does it mean, hexadecimal? Hexadecimal means 16. Okay, if you count the number of digits in the hexadecimal number system, you'll find that there is a total of 16 different symbols. Okay, so 0 to 9, there is 10. So this one is 11, 12, 13, 14, 15, 16. There are a total of 16 symbols in a hexadecimal number system. Okay, so hopefully that makes it clear on how these different number systems are different and what are the symbols and what's the name. So that's what I'm trying to convey in this slide over here. Next, so far, any question on this one? Are we good? Are we good with this?
Good, sir.
So if you have any question, please feel free to just type in or just voice out. All right, let's take a look at how to write this number system. Right. So over here, I have a number over here. The number is 1596. So 1596 is the number, and I have a smaller font over here and it says 1010. Okay, so this is how we write them. So this is known as the radix, or this is the radix is another name for the base number. Okay, base number. Base number. Okay, so this base number is 10, or in other words, we can also say radix 10. So that's a new word to you. Radix 10, base number 10, same thing. So this denotes that it is in a base number 10 format or decimal format. And the number that's large here, these are the value. Okay, so I have over here 1596 in base 10 or radix 10. That is how we write it. This is the notation. Okay, get familiar with this. Now, what about this? Okay, so over here we have 1011. That is the value. And what form is this? Look at
binary.
Yep, exactly. So if you take a look at the number over here, it's radix 2. In other words, it's a binary form. Okay, right. Now, a tricky one over here. So we have this number. It's not looking number. It's like a value over here. This value is AF81, and the form is in hexadecimal form. Okay, hexadecimal, or you can write it this way: R equals to 16. Okay, or base number equals to 16. Okay, the same thing. So this is the value AF81 and in the base 16 form. All right, so hopefully that is clear how to write this number in different number system. One is value and the other one is the base number or the radix. All right, so in this course, we are going to dive in even more narrow. So we have many number systems, binary, we have decimal, octal, and hexadecimal, right? But in digital logic, we are just going to focus on binary numbers, okay? Binary numbers. So we are not going to talk a lot about other number system from this point on. Okay, so for example, this is a 4-bit binary number. So this is a new term also that I want to introduce to you guys. For a binary number like this one, so this individual digits, they are known as bits, B-I-T. Okay, bit is 1. Okay, if you have many, it's called bits, B-I-T-S, bits. Okay, so this is and for this, over here we have 4 bits binary number. Okay, and for this bits also, we have a special name for this bit that is like the most left over here. And this bit over here is special because we call it the MSB, or in other words, is the most significant bit. Okay. So most significant bit, which is the bit at the leftmost. What about the bit at the other end? The bit at the other end is called LSB. So LSB is the opposite of MSB. So LSB stands for least significant bit. Okay, least significant bit. Most significant bit, least significant bit at the opposite end. Okay, so just to make it clear, so if I have a number like this, which one is the most significant bit? Most significant bit, or MSB, will be the one that is the most left, which is this guy over here. And the least significant bit will be at the other end. So this is the LSB, and this is the MSB. So hopefully that is clear, because going forward on this point, we will just talk about MSB and LSB. So make sure you're clear about what they are, because they have different roles. Later on, you'll see. Right. So this is another example. So this is a, how many bits is this? This is an 8-bit number. If you count how many digits over here, you have 8 digits. So you have 8 bits. Okay, 8 bits. And this is another term that I want to introduce to you guys, and that is known as nibble, N-I-B-B-L-E. So nibble is a group of 4 bits. So if you have 4 bits, like this is a group of 4 bits, this is known as a nibble. Okay, and over here we have another nibble. Okay. Okay, and we have over here 8 bits. Okay, which one is the MSB? So this guy over here is the MSB, and this one over here is the LSB. Okay, is that clear? All right. So that's the PowerPoint slide. Okay, for your information, this scribbling is only visible on the video that I am recording right now. So if you open the PowerPoint slide after this, you will not see the things that I am scribbling over here. Okay, so all you will see is a clean PowerPoint. Okay, so if you really want to see what I write on the PowerPoint, you can refer to the video. Okay. Okay. All right. So this is some definition and the terms. Okay. Now we're going to do something much more interesting, that is counting. Okay, so over here, what we have is a decimal number system, and then we want to count. So this is something that we've done from since we were a kid. So we are told that we start counting from 0, and then this 1 and 2, 3, 4, 5, 6, 7, 8, 9, and then it goes to 1, 0, or we call it 10, and then we call it and then 1, 1, 11, 12, and so on and so forth, right? Okay, now we are going to do that for other number system as well, and I need you guys to focus on this one, because some of you might get lost in between, because I know some last semester I think a good amount of the class actually got confused on this one. Okay, so now we are going to do the same counting but this time we're going to do it on the octal number system. Okay, so let's do this together with me. Now we are going to start in the octal number system. We start with 0, and then we have 1, and then you count up, right? You add 1 to that, and then you have 2. Okay, we have 3, you have 4, 5, 6, 7, Now, question. What's the next digit after 7? We have 8, right? Then we have 9, right? Is that? It's not 8, it's not 9. Because in the octal number system, this digit 8 and digit 9 onwards does not exist. Okay, if you look at, let me show my previous slide over here. If you look at this slide over here, okay, take a look at this. In the octal number system, these are the digits that are allowed in the octal number system. So the minimum one is 0 and the maximum one is 7. There's no such thing as 8. There's no such thing as 9, 10, and so on in the octal number system. Okay, so that's the problem, right? So how do you write like bigger numbers in octal number system? Okay, that is what we are going to answer over here. So, okay, there is no 8, there is no 9. So what is the digit after 7 in octal number system? It's going to be 1, 0. Okay, right. Thanks for that, Vinesh. Yes, you're right. 1, 0, 10. Or okay, I like to call it 1, 0 because I don't want you guys to confuse with this 10 over here. Okay, I'll say 1, 0. Okay, what about after that? We have 1, 1. Okay, after that we have 1, 2, 1, 3, and then we arrive at 1, 7. What's the next digit after 1, 7, right? It's going to be 2, 0. Okay, so I hope you're beginning to see the trend over here. So we start with single digit over here, and then we run out of symbol for a single digit, and now we start with the 2-digit number over here. 2 digits over here. Okay, but now we start with 1. Okay, we start with 1, and then 1, 0, and then 1, 1, 1, 2, 1, 3, and then we start until we run out of this until 1, 7. There's no more possible combination in this one anymore, and then we start with 2, 0, and then we have 2, 1, 2, 2, so on, 2, 3, 2, 4, 2, 5, 2, 6, and then we arrive at 2, 7. So what's next? This is the 2s. The next will be 3, 0. Okay, and 3, 1, 3, 2, and so on. Okay, you get the idea, right? That is how we count in octal. Is that clear, everyone? Is there anyone who's lost? If you're lost, I understand, because this idea, it might be strange. Okay, nobody has issues?
Okay, sir.
Okay, wow, I am impressed. Okay, very good. Okay, that is octal number system. Now, let's try to do the same for another number system. Okay, let's try to do for binary. Okay, binary, right? So remember, in binary number system, there's only 2 allowable digits. It's 0 or 1 only. Now, what's the next number, right? Okay, let's do the counting over here. Let's go ahead and go to this slide, counting. Okay, so we start with number 0. Okay, fine, no problem with that. And number 1 over here. Okay, that is the total digits that's allowed in binary number. So what's the next number after 1? That's the question, right? Anyone? This is going to be interesting, but it's
1, 0.
Yes, it is. Because we run out of combination for a single digit number, we are going to have a double digit number, but we start with 0. And then it's going to, the next number is going to be 1, 1.
1, 1.
You take your time to digest this. Okay. Now, is there any other possible number for 2 digit, like 1, 0 and 1, 1? After that is
1,
there's
0.
no more. Yeah, there's no more possible combination over here with 2 digits. So we need to add digits. So now the next number will be 3 digits. And it will be 1, 0, 0. Okay. Now it's going to get a little bit more tricky over here. After that, what's that? What's next? Yeah, 1, 0, 0. And then the next number will be 1,
1, 0,
0,
1.
1.
0, 1.
Okay, good. And then we have 1,
1,
1,
1,
0.
1, 0.
Yes, and you have 1,
1, 1,
1, 1. Yes, you're following it. Hopefully everyone else is also following, right? And then we have 1, 0, 0, 0.
Zero.
Yeah. So you get the idea. Yeah, you get the idea. And at the end of the day, like we can keep on counting like forever. Okay, but this is how the trend goes. Okay, so that is decimal done, octal done, and binary done. Okay, simple, right? Now, I'm going to show you to something even more strange, and that is how do we count in hex? Okay, so in hex, let's take a look at that hex table. Hex stands for hexadecimal, right? So hexadecimal is just too long. Most people would just use the short form hex. How do we count in hex? So take a look at this hex. For hex, the total symbols that's allowed in hex is many. There are 16 in total, and there are like alphabets even in hex. Okay, so let's do the counting and see how do we count it in hex. All right, let's start with, as usual, we will start counting from 0. So we have 0, we have 1, we have 2, so on and so forth until we arrive at 9. So what's the number after 9? 10. The number after 9 is, it's not the number, a symbol after 9 is 8. Okay, because in hex there is such thing as an A. Okay, right? And after A, it's B, it's C, D, E, and F. After that, what do you have? You have G. There is no such thing as G in hex. So by the time we reach F, we already ran out of symbols for a single digit, right? So now, what the next number after F would be 1, 0. Okay, and then it will be 1, 1, and 1, 2, and 1, 3, 1, 4, so on and so forth. 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, 9. What's next? 1, 8. Is that strange? Yes, I think it's strange. The first time I came across this, I was like, wow, mind blown. I never thought that we can count in this way. But that is how computers keep records, keep numbers. Okay, we have 1A, and then we have 1B, so on and so forth, and until we arrive at 1F. Is there any other possible combination after 1F? No more. And then let me just write a new row over here. We arrive at 2, 0. Okay, is that clear, everyone? And then we have 2, 1, 2, 2, until we have 2, 9, and then we have 2, 8. Then we have 2, B, until 2C, 2D, 2E, and then we have 2F. Then there's no more possible number over that. Then we are going to go for 3, 0. Okay, is there anyone who's confused? Let me take a sip of water. If you're confused right now, no problem. When you're confused, it's a sign that you're learning something new. So I really encourage you guys to, I'll be posting additional videos like before the class and after the class. So you guys can check out those videos so that to clear your confusion. So my recommendation would be, if you're confused, clear the confusion like as soon as possible, because the longer you wait, the harder it's going to clear the confusion, right? If you don't really understand what this is about, if possible, like clear it out by today. Okay, but I'm going to try my best to clear this confusion by the end of this class. But we don't have like forever. We don't have the entire day. You guys also have some other classes. So if after the class you guys watch the video and still it's not very clear, please get back to me as soon as possible, because like it's going to be tougher if like at the end of semester you're telling me, oh, I was confused with number system, because if you don't understand number system, the next topic is going to be harder to understand, and then it's going to be harder and harder and harder and harder. Okay, so do clear out this confusion as soon as you can. All right, let's continue on with our counting. So this is a table showing how we count. Okay, we have over here r equals to 10, radix 10, so we count as usual, 0, 1, 2, 3, 4, 5, and so on. So if you have r equals to 8, so this is how we count. So this is exactly what we did just now, 0, 1, 2, 3, 4, 5, 6, 7, and after that it jumps to 1, 0, 1, 1, 1, 2, 1, 3, because there isn't number 8 over, there isn't a digit symbol 8 over here or 9 over here for octal, right? For radix 2, this is also what we did just now, and for radix 16, this was what we did just now. So start counting, right? Okay, right. So the thing that I would like to convey over here is the equivalent value. The equivalent value. Okay, for example, let me just take this row over here. So if I have number 2 in decimal system, it is equivalent to this in binary system. Okay, is that clear? Okay, so you can imagine like okay, I say eat, E-A-T. Okay, eat in English. Can I say the same thing in Bahasa? I can, right? It's called makan. It refers to the same thing, the same action, but they are in a different language. Is that clear? Okay, so in the same way, over here, this value and this value, they are equal. They refer to the same thing, but they are expressed in a different number system, different language. Okay, so you might write like this 2 in base 10, but in base 2, the value is like this. Okay, let's take a look at another example. Now, let's take a look at maybe over here, this row over here. So if I have the value 8 in decimal number system, if I want to write the same value, the same number, but I want to write it in a binary format, it is this over here. Okay, but if I want to write it in a octal format, it is this value. Okay, so don't be deceived by this number over here. Okay, that's the reason why I don't say this is 10. This is 1, 0. So I don't want you guys to confuse this 10 with this 10 over here. Okay, so 8 in decimal is equivalent to 1, 0 in octal. Is equivalent to 1, 0, 0, 0 in binary, and is equal to 8 in hexadecimal. Okay, so let's take a look at one more example. Let's take a look at this one. This one's more interesting. 13 in octal is equivalent in value to 1, 5 in octal. It's equivalent in value to 1, 101 in binary, and is equivalent to D in hexadecimal. Okay, so it looks different, but the value is the same. It's just like what I said just now. I might speak different language, but I can convey the same intention. All right. So, but there's a problem over here with this table, right? So what if I have a number in decimal, and my number in decimal is 100,1596. Okay, what if I have this number, right? And I want to know what's the value in binary. We'll be in trouble because this table is going to be gigantic. Like it's going to be a big table if you're going to rely on this table alone. Okay, so that is why in the next slide we are going to see how we can convert one value from one number system into another value in another number system. Okay, and that is what we call base conversion. Okay, base conversion. So base is the base number, base 10, base 2, base 8, base 16, and we can convert them we can convert them between one another. So from base 10 we can convert to base 2. From base 2 we can convert also to base 10. Okay, so today we are going to take a look at how we are going to convert from base R to decimal. Okay, what the heck is base R, right? Okay, R is just it's just a notation that I use. So R can be, okay, it can be base 2, can be base 8, can be 16. Okay, so you can convert from 2 to decimal, okay, or this is 10, right? So you can convert from base 2 to base 10, can convert from base 8 to base 16, base 8 to base 10, base 16 to base 10. Okay, that is what we're going to take a look at. And to do that, we are going to do something called the weighted sum. Okay, so weighted sum, I think it's kind of familiar to you guys also. Weighted sum, it's just expanding the number in polynomial notation and adding all the terms. And you'll be like, what is that? All right, so I bet like some of you might be startled by all this strange looking term. Okay, so if you're not confused, it's okay. Very good. I applaud you because you remember what you learned in calculus and before this. But if you guys are not sure what is weighted sum all about, I'm going to briefly and quickly cover it again over here. So using weighted sum, it allows us to convert from binary, octal, and hex into decimal. Okay, weighted sum, right? WS stands for weighted sum. Let's take a look at how we are going to do this. Okay, so first, take a look at an example over here, binary to decimal, and we are using weighted sum. So say, for example, I have a number in binary over here, okay, or in base 2. How do I know it's base 2? It's given over here, the radix is 2. Right, so how do I do weighted sum? Okay, here's how. It's easy. Okay, so for each number in this digit, we are going to assign a weight. Okay, so okay, let me hide that first so that it's easier to see. Okay, so for each digit over here, we are going to assign something we call the weight. Okay, so at and the weight at each position is different. So the weight at this position is going to be 2 to the power of 0. The weight at this position is going to be 2 to the power 1. The weight at this position is going to be 2 to the power of 2. Okay, so and if you have more digits, the weight adds up. It just continues adding, right? So it's going to be 2 to the power of 3 over here, and then so on and so forth until you have 2 to the power of 7 and 2 to the power of n. Okay, n can be any number. Okay, but we are not going to take a look at that because we only have 3 digits, 3-bit number over here. So it ends over here. So how do we take the weighted sum of this? So the weighted sum is easy. So we take the number itself and we multiply it with the weights. Okay, so here's how it goes. So we take the number 1 and we multiply it with the weight. The weight is 2 to the power 2. Okay, that is for this one. What about this one? We do the same. Yes, we're going to add them together because it's called weighted sum. So we're going to add that to 0 times 2 to the power 1. Okay, and we're going to add that to the last digit over here, and that is going to be 1 times 2 to the power 0. So what do you get? So 1 times 2 to the power 2, that is 4, plus 0, because anything times 0 is 0, plus 1 times 2 to the power 0. What's 2 to the power 0? 2 to the power 0 is 1. Okay, right, and the total will be 5. That is how we do weighted sum. Now the question is, this 5 is in which base? This 5 is in base 10. Okay, so in weighted sum, whatever you do is going to result in base 10. So that is the thing that I show you guys here. So any number system over here, you see, if it goes through weighted sum, it's going to end up as a base 10 number. The base 10 number. Okay. All right. That is binary to decimal. Base 2 to base 10. Okay. So far, anyone has question? Are we good? Okay, right? All right. So let's try this one. So everyone, if you have a pen and paper, the best way is to do this together with me so that you get it instantly. You don't have to wait for like after the class or something else, because it's going to get harder to do it by yourself. Okay, right. So if we have this 1, 1, 1, 1, so I'm going to do the same thing. I have weight over here, 2 power 0, 2 power 1, 2 power 2, and because we have one more extra digit over here, we have 2 power 3. Okay, so my weighted sum would look like 2 power 3. Okay, I can write it 1 times 2 power 3 plus 1 times 2 power 2 plus 1 times 2 power of 1 plus 1 times 2 power of 0. Okay, so like if you notice, like anything times 1 is just the same value, right? So you can also just write this like this, 2 power 3 plus 2 power 2 plus 2 power 1 plus 2 power of 0. So 2 power 3 is 8, 2 power 2 is 4, and 2 power 1 is 2, 2 power 0 is 1. And then the sum you get, 8 plus 4 is 12, 12 plus 2, 14, 14 plus 1,
15.
15. Yes, good job. And the base number is base 10. Okay, clear, right? Hopefully that is very clear on how do you do that. So now you can have any number. So you can do, can you do this like 1 0 1 1 1 1 1 0 1 1 0 1? Okay, I can say that, okay, now convert this into a base 10 number. Right? Can you do it? Yes, you can, by using weighted sum. So in the next class, be prepared for this kind of quiz question, right? Okay, that's just a hint. So far, any questions before we proceed on to the next base? Okay, no question. I'm gonna take it that it's okay, right? So the answers are on the slide. If you want to try it out after this, you can do that. Okay, you can also try this one out later. Okay, yes. Let's say if you want to do some practice, you can always verify the conversion by using your calculator. If you have scientific calculator, you can do the conversion, and then it will give you the answer as well. Okay, so far, is anyone writing any message? Okay, let me check that. Okay, no one. All right, so far we have seen, okay. All right, so what about the case that we have this kind of dot? Okay, usually we say this is a decimal point, right? But this is not a decimal number system, so we don't say, we don't call this a decimal point. We call this a fractional point. Okay, fractional point. Okay, what about this? If you have like a fractional point like this, how do we convert this into decimal? Okay, it's the same thing. We are going to use weighted sum as well, but there is a trick to this. Okay, let me show you what's the trick. So previously we assigned weights to each one, right? So we assign weights to we assign weights to each digit over here, right? So in the event you have this fractional point over here, what you want to do is to start assigning weight from the fractional point over here. So your weight starts from here: 2 power 0, 2 power 1, 2 power 2, and 2 power 3 over here. Now, what about the weights like after this, to the right of this point over here? Is going to be negative power. Okay, negative 2 power minus 2. Okay, so that is how we solve this kind of conversion number. So at the end of the day, what you have is 2 to the power 3 plus 0 times 2 power 2 is 0. I'm not going to write it, so I'm going to write this 2 power 1, 2 power 1 plus 2 power 0 times 1 is 2 power 0. I'm going to have 2 power minus 1, 2 power minus 1, and I'm going to have 1 times 2 power minus 2. Okay, so what do you have over here? You have 2 power 3 is 8, and 2 power 1 is 2, 2 power 0 is 1. And what about this one? This one is equivalent to 1 over 2 power of 1. So which is that, and this one is equivalent to 1 over 2 power of 2, which is 4. Okay, so there you have it. You have the answer to be 8 plus 2, 10, 11, 11.5, 11.75. That is how we convert numbers or binary numbers that has this fractional point. Okay, that is one thing to take note about. All right, that is binary to decimal. Right. So we're going to cover a little bit more, and then we'll end our class today. Right. So we talked about binary to decimal, and now we're going to talk about the next one, which is octal to decimal, and then we're going to talk about hexadecimal to decimal. And good news is they all use weighted sum, so they all work in the same way. Okay? It's just a slight difference. I'm going to show you what the difference is, and then you can do that on yourself. All right. So let's say right now we have this number. We have this number, and the number is 75 in octal. And I tell you that, okay, now please convert this number to a decimal form. So what do? We assign weights, right? Okay. So what do we do? Just like in the previous example, we assign weights. So we assign weights 2 to the power 0, and then we assign weights 2 to the power 1. Oh wait, is that right? Okay, it's not right. It's not 2 to the power 0 and 2 to the power 1, because this time, what's different? Previously, we have binary to decimal, right? And because the original number is binary, but that's why the weight is in 2 to the power of something. But now we don't have a binary number, we have octal number. So the weight is going to be in terms of 8. Okay, so over here we have the weight also. We have 8 to the power of 0, and then we have 8 to the power of 1. Okay, so once we have this weight, and the next thing to do is just the weighted sum. So we have 5 times 8 to the power 0, which is from here, and 7 times 8 to the power 1, which is from here. Okay, so this is going here, and this is going here. And at the end of the day, that is how you arrive at 61 in base 10. Okay, same thing. The only difference is the weights. Right, so let's take a look at another one. So, okay, so we have, let's say, now, can I do the same thing? Like, let's say I have 75, and I have a dot over here, and dot 2, 3. Can I convert that into a base 10? Yes, I can do that also. It's the same way. I assign weights to this, assign weights to this. Let me just try to use different colors so that it is not as confusing. Okay, so this is the weight for this place, it's weight for this place, and this is the weight over here, minus 1, remember, 8 to the power of minus 2. Okay, and then you do the weighted sum, and then you arrive at a answer. Okay, this is just an additional example that's not in the slide. I just thought about showing this. Okay, so now hopefully you are beginning to see what's the difference between binary to decimal and octal to decimal, right? Weighted sum with slight difference. Right, now we're going to cover the last one today, and we're going to end our class. Now we're going to see how do we convert from hex to decimal. Hex to decimal, it works in the same way. It works in the same way. So for example, I have this 2-digit hex number over here. We have FF, and okay, switch this. We have FF in base 16. Now I'm going to change this to a base 10. So we are still going to use the weighted sum, but what's different this time? The difference is going to be in the weights. So the weights over here will be 16 to the power of 0, and over here will be 16 to the power of 1. Okay, now then we do the weighted sum, right? Okay, you're like, oh, okay, weighted sum is simple, but then you realize that, oh my god, like, how do you multiply f with 16? That's kind of funny, right? Okay, so how do you do this multiplication? So the trick is easy because this is a alphabet, right? So you need to convert this alphabet into its equivalent number form. So F is equivalent to what number in decimal? So if you take a look at like this table, I'm gonna show you to that useful little table again. Yes, this one. Take a look over here. We have F in hex, and the equivalent of F is 15. So we are going to take this value 15 and do that multiplication. Okay, so let's go back here. All right, so that is how we arrive at before that, so we are going to write here 15 times 16 to the power 0, and over here is 15 times 16 to the power 1. Okay, so that is how we arrive at 255 base 10. Okay, so are you guys following? Is this still okay?
Okay, sir.
Okay, so can I do this? Okay, so if I have a number like this, we can also do the same conversion, right? The trick is, remember, there is a fractional point over here, and you assign your weights following the fractional point. So you assign the weights over here, 16 to the power 0 here, 16 to the power 1 here, and over here, because it's after this fractional point. Okay, and so on. That's -2. Okay, and then you do the weighted sum, and then you would arrive at an answer. Okay, so do expect this kind of a quiz in the next round. All right, so let's take a look at what we did today as a recap. So today, what we did was I've introduced to you guys the number system. So I've introduced to you guys what is a number system, how are they different. So there is 3 types of number system: binary, we have decimal, we have binary, we have octal, we have hexadecimal. These are the 3 new number system. Okay, decimal number system is the one that you're familiar with. So if you include that, there is 4 number system. So number system is just like language, but for computers. That's what we covered today, and that is also the way computers talk to one another. And in the beginning of the class just now, we have also covered this binary, octal, decimal, and hexadecimal, how to count them and how to write them. We've covered this in the beginning of the class, and we've also talked about bits. What are bits? What's MSB? What's LSB? And how are they different? And these are the new terms, nibbles. And we've also tried to count just now. And we've also come across this table. This table just shows an equivalent value table. So you don't have to memorize this table, but it is very useful to have. So previously in the exam, I always tell my students to, okay, first thing in the exam, write this table down so that you don't have to do the calculation for simple numbers, and that reduces the mistake. Okay, so this table is going to be very helpful, especially if you are beginning this chapter. By the end of this course, by the end of this semester, this table is going to be like at the back of your head. Like you can just spit out, okay, what's 9 in hex, or what's 9 in binary, what's 9 in octal. Like you can just memorize this number out by the end of the semester. Okay. Okay, and we've also covered how to convert numbers from 3 different number system to the decimal number system by using a weighted sum method. So that is what we have covered today. So I hope that you guys will not stop here. After this, the lecture, I am going to upload the this recording is going to be in the channel, and on top of that, I am also going to post additional videos to reinforce your understanding. And in the next class, next week, we are going to continue, and you can expect a quiz based on what we have covered in this class today. All right. So, is there any question before we end our class today?
Sir,
Yes.
so the table will not be provided, right? That means we'll have to know it by heart, lah, right? The table, just now, conversion table.
It's in my slide. I will provide this slide to you guys after this class. So of course you can refer to the slide, but I will highly recommend you guys to try to memorize them because it's going to be very helpful in the next topic. All right. So it's going to make you much quicker. So it is. I do recommend you memorize them, but even if you don't memorize them, it's still okay. So I realized that last semester I told nobody to memorize them, but because they did the practice, they did the quiz and so on, these came in, they automatically to them. But if you have the time, do try to remember them. Okay.
Okay. Thank you, sir.
Yeah. Right. Any other question before we end our class?
No, sir.
No question? Okay, if you do have any other question, please feel free to stay back after this session. I will stay back also. If there's any one of you here, I will answer your question. I will answer things that you're not clear about. And if there is no other question, then I'll see you guys again. Take care. Bye-bye. I'll stop the recording.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Right, you're
Thank
welcome.
you, sir.
Thank you, sir.
Thank you, sir.
Okay, thank you, sir.
Hello, sir. Are you still there?
Yes, I'm still here.
I have a question, sir.
Yes.
For the example, 75.23 base.
Okay.
8. The octal to decimal, yes, that one.
This one.
Ah.
Yes.
For
What's the
the
question?
final answer,
Yes.
should we write in fraction or point?
What do you mean in fractional point? Isn't that the same thing?
Oh no, mean final answer I got the 3,000. Should I write it that way or should I write it?
I'm losing your voice. I couldn't hear what you were saying. 3,000 something you were saying?
For that question, the example.
Yes. Yes.
My final answer, I got 3,923 over 64.
3963.
3923
923 dot
over 64.
over 64. Okay.
Should I write it that way or should I write it right in like 61.296875?
Yeah. Your of course this is not wrong. The value is right, but the format we're talking about this kind of format over here.
Okay, so
yeah. So the value would be 3923 like dot something, right?
Oh no,
Yeah.
they can say 61.296. So should be like that point.
Yeah, and also remember to write the base number.
10.
Yeah.
All right.
Because if you don't write the base 10, like it can be other base as well. People can misinterpret this as other base. Okay.
Okay.
Sir,
Yes.
I also want to ask the same question about this answer. Actually, in fraction, it said like this. But if I change it to decimal point, it showed me like 61.296875. So the decimal point, how much I should take? Like, is it 2 decimal point or 3 decimal point? When I want to write in fraction decimal point.
Okay. Actually, I'm not very particular on that.
Okay.
Yeah. So as long as it is for me, most of the time I'll take like 2. 2 points, like 2 numbers over here most of the time, right? But yeah, you can do more if you want, but you cannot go on like that, right?
Yeah. Okay.
So
Okay. Thank you, sir. Thank you.
all right.
Okay, thank you.
All right, that's all. Okay, thank you very much. See you soon.